Hello everybody, my name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to my series of lectures on the course control system. In today's lecture, I am going to discuss the concept of block diagram reduction technique. Block diagram reduction technique is a pictorial representation of any control system. So in this representation, the block diagrams represent the relation between input and output of an entire system. Any complicated system we can easily represent by means of connecting different blocks. And in this block diagram reduction technique, every block is arranged in a sequential manner. So the various elements that we are going to use in block diagram reduction technique, first one is a summing point, second is a takeoff point or a pickoff point, thirdly forward path, and lastly fourth is a feedback path. So we'll see one by one what is the significance of each element. So summing point, so when I need to add or subtract more than one signal, then we use this summing point. So it is generally represented in this manner. Next, the takeoff point is generally used where we want to take any signal for any practical use. So here this, as shown in that diagram, this is the point where I am taking a feedback from the output. So this point we call it as a takeoff point. So next is the forward path. So this is the direction of the forward path. So the direction of flow of signal from input to the output, we call it as the forward path, and the direction of flow of signal from output to input, we call it as feedback path. So these are the four basic elements that we are going to repeatedly use in our block diagram reduction technique. So these are the some of the advantages of block diagram. It facilitates an easy representation of any complex system. So we have facility to easily access to individual elements of any complex system, and which is represented in terms of block diagram. Next, the entire functional operation of the system can be observed from the block diagram representation. So the performance analysis of any complex system can be easily simplified using block diagram, and we can easily calculate the overall transfer function, however complex the circuit may be, easily by means of block diagram. The main disadvantages of block diagram is there is no unique representation of a given system using block diagram reduction technique. In this, the source of element and the source of energy in the system is not shown in block diagram representation, and lastly, it does not give any information regarding the physical construction of the system. These are some of the applications of block diagram. It is used in hardware design, electric system design, used in software design, process flow diagram, is used in determining the transfer function of the system, and it is also used to find the stability of the system. Next, we are going to discuss the rules that we need to implement in block diagram reduction technique. One must remember that the expression for C of S must remain same before and after applying the rule. So the first rule is blocks in cascade. So either in cascade or in series. So here the input is R of S, the output is C of S. Okay, so these two blocks have the gain G1 and G2. So in this case I can write C of S is equal to, input is R of S, and it is getting multiplied by G1 and G2. So these two blocks G1, G2, if they are in series, I can replace that by a single block of gain G1 and G2. So here also, as you can see, the expression of C of S will still remain same. The input is R of S and the block gain is G1, G2. So one must remember that before and after applying the rule, the expression for C of S should always remain same. Coming to this second rule, the blocks in parallel. So here both the blocks G1 and G2 have the common input R of S. So R of S, so this is the expression for C of S, which is R of S into, so G1, the polarity is plus or minus, G2 plus or minus. So both blocks are getting added to the same summing point. So it is plus or minus G1 plus or minus G2. So these two blocks I can replace by a single block. So here also input R of S is getting multiplied by G1 of S plus or minus G2 of S, which will give me the expression of C of S. The third rule is eliminating feedback. So here input is R of S, output is C of S, forward gain is G, feedback gain is H. Here I have two types of feedbacks, one is negative, one is positive. Remember, when it is negative, you get positive sign in the denominator. If it is positive feedback, I get a negative sign in the denominator. So upon eliminating the feedback loop, the formula that we need to replace for feedback loop is G of S. It is G of S divided by 1 plus or minus G of S into H of S. Remember, this formula will have positive in the denominator for negative feedback and negative in the denominator for positive feedback. Yeah, associative law. So before I apply the rule, you can see here I will need to write the expression for C of S, isn't it? Now R of S signal is getting added by the signal X. So R of S plus or minus X. So this will have R of S and this will have plus or minus X. So here I will get R of S plus or minus X, and again that signal is getting added to by another signal plus or minus Y. So plus or minus Y. So that will give me the expression of C of S. So according to associative law, when I have two summing points adjacent to each other, I can interchange both the summing points. Okay, so here I have interchanged both the summing points. Here also, if I need to write the expression of C of S, you can write R of S. So R of S is getting added by plus or minus Y, and then again it is getting added by plus or minus X. So in both the cases the expression is same. Okay. The fifth rule is shifting takeoff point before block. So this shifting, before shifting, let us try to write the expression for C of S. So it is C of S is equal to R of S is getting multiplied by g. So it is r of s into g, and this is your takeoff point. So x is equal to, so takeoff point is taken near the output, so x is nothing but c of s, which is also equal to r of s into g. Now my aim is to shift this takeoff point. Okay, so this takeoff point I need to shift before the block G. So I have shifted this takeoff point before G. So in this case, let me write the expression for C of S. C of S will be same R of S into G. There is no change in C of S. I need to write the expression for X also. X is equal to, in this case, it is R of S. We can clearly observe that the expression of X previously and now are not one and the same. So for these two signals to become equal, I need to multiply X by G. So I will multiply by G, as you can see. So by this we can say that if I need to shift my takeoff point before a block, I need to multiply by the gain G. So in this case it is G. So in a particular sum, this G can be of any form. Rule number 6. Now my aim is to shift this takeoff point after the block. Okay, so before I shift my takeoff point, let me write the expression for C of S. C of S will be same R of S into G, and X value will be R of S. Now I need to shift my takeoff point after the block. So I have shifted the takeoff point after the block. Here also C of S in this case will be R of S into G. But the value of X is nothing but C of S into C of S, which is R of S into G. So here both are not one and the same. My X need to be only R of S, not R of S into G. So in order to eliminate G, it will be sufficient if I multiply this by 1 by G. So if I want to shift my takeoff point after the block, I need to divide by the gain of the block after which you are shifting your takeoff point. Shifting summing point before the block. So before I shift, let me write the expression of C of S. It is R of S into G, and for that you are adding your X value, isn't it? So it is plus or minus X. Okay, so that is the expression for C of S. Now I need to shift my summing point before the block G. So I have shifted. So in this case also, let me write the expression for C of S. So C of S will be, here input R of S is getting added by the signal X. So R of S plus or minus X, and that is getting multiplied by G. So if I expand my expression of C of S, which will be R of S into G plus X into G. So you can see that the first term in both the cases are same. Okay, here also I have R of S into G, here also R of S into G, but the second term previously has only X, but now it is X into G. So for both expressions to remain same, this I need to multiply by the second term. So the second term needs to get multiplied by 1 by G. So for me to shift any summing point before the block, I need to divide my takeoff point or multiply my takeoff point by 1 by G. shifting summing point after the block. So here also let me write C of S expression will be R of S plus or minus X, and that gets multiplied by G. So this is R of S into G plus or minus X into G. So now I need to shift my summing point after the block. Let me write the expression once again. So in this case, C of S will be R of S into G, and that is getting added plus or minus X. So here, as you can see, the first term in both the cases are same, R of S into G, R of S into G. Here I have X into G. So here I have only X. So the second term needs to get multiplied by G. So in order to shift the summing point after the block, I need to take my summing point with the gain of the block G. And last rule is splitting summing point. So if my summing point has more than 2 inputs, I can represent this by splitting a single summing point into 2 summing points. You can clearly see this in previously the expression will be C of S is equal to C. For R of S it is plus or minus, so simply it is R1. For R2 it is minus plus, so it is minus plus R2. Again for third input it is again plus or minus, so it is plus or minus R3. So here also let me write the expression for C of S. So R of S it is plus or minus, R2 it is minus or plus, and again it is R3 plus or minus. So the expression is remaining same. So one single summing point I can, if it has more than 2 inputs, I can split into 2 summing points. So these are the rules that we will implement in our block diagram reduction technique. So let us now, based on the 9 rules that we have discussed, let us see some of the tutorials based on the block diagram reduction technique. So we need to apply those rules whenever necessary in order to solve tutorials on block diagram reduction technique. So here we need to determine the overall transfer function using block diagram reduction technique. Remember that while applying any particular rule to a given block diagram, the complexity of the block diagram representation should reduce when compared to the previous step block diagram reduction technique. Okay, so here in my first step, as I can clearly see that this is a feedback loop and this is also a feedback loop. Okay, so I'll try to first step implement these two. So we know the formula, isn't it? That is G by 1 plus G into H. So in place of G I have here G2, in place of H, so since there is no element here, the value of H is 1. And in second case, in place of G I have G5, and in place of H I have H5. Since both are negative feedback, I'll get positive in the denominator. So let us try to replace this by our formula, that is eliminating feedback loop. So we know that this will become G2 by 1 plus G2, and this elimination will give me G5 by 1 plus G5 into H5. So these two I am going to replace by the respective blocks. So next we can see that this block and this and these three blocks are in cascade, isn't it? So in the next step we'll apply the rule number 2, that is blocks in cascade. So just we need to multiply these three gains present in blocks. So that will give me G2, G3 and G5 divided by 1 plus G2 into 1 plus G5 into H5. So clearly this is nothing but this, upon seeing we can say that this is an elimination of feedback path. Okay, so here in play the formula, as you know, it is G by 1 plus G into H, isn't it? In place of G I have this entire block gain, in place of H I have 1. So upon, so that is G by 1 plus G into H, so H is 1, isn't it? So upon taking LCM and simplifying, that will give me a value as G2, G3, G5 by 1 plus G2 into 1 plus G5 H5 plus G2, G3, G5. So these two blocks in the finally are in cascade or series. So that will give my overall transfer function as G1, G2, G3, G5 divided by 1 plus G2 into 1 plus G5 H5 plus G2, G3, G5. Coming to the next sum. So here also I need to find my overall transfer function using block diagram reduction technique. So here the first rule that I can apply is by shifting this takeoff point after the block G1. So let us recall rule number 6. So when I shift my takeoff point after the block G, the takeoff point needs to get multiplied by 1 by G. So here also I'll do the same thing, since here in place of G I have G1. Okay, so I should multiply the takeoff point. So this is the takeoff point here, isn't it? So here I need to multiply by 1 by G1. So in the takeoff point I have multiplied 1 by G1. Already G3 is there. So these two blocks will be in cascade. And this is nothing but eliminating feedback loop. I can apply more than one rule in one step. Okay. So since these two blocks are in cascade, that will give me G3 by G1. Since this is feedback elimination, that will give me the formula G1 by 1 plus G1 into H. So here I can see that these two blocks are in parallel. So both the input of both the blocks are same. Both are going to the common summing point. Both are positive. So we know the formula that it is G1 plus or minus G2, or strictly speaking it is plus or minus G1 plus or minus G2. Since we have only positive, so that will give me G2 plus G3 by G1. So these two blocks are in cascade. I just need to multiply these two gains. That will give me overall transfer function as G1 G2 plus G3 by 1 plus G1 into H. The third sum, here also I need to find my overall transfer function. So here I can shift this takeoff point after the block G2. Okay, so that these two blocks can become cascade and I can eliminate a feedback loop. So you should get that idea. So after applying rule, is it any possibilities there that my block diagram is getting the complexity of my block diagram is getting reduced or not? First you need to check before applying any rule. Okay, so here let me erase this. So in the first step, I am shifting my takeoff point after the block. Let me give you the rule number 6. So after shifting the takeoff point, my takeoff point should get multiplied by 1 by g. So here takeoff point has two feedback loops, isn't it? So here we will get 1 by g3, and here also I need to replace 1 by g3. So in the next step, I have multiplied 1 by g3 in both the feedback loops that are connected to this takeoff point. And the next steps are very obvious, isn't it? So these two are cascade, which will give me h1 by g3. These two blocks in cascade will give me h2 by g3, and these two blocks which are in cascade will be g2 into g3. So that I'll replace, and this entire block we can see that they are forming a feedback loop, isn't it? G2 G3 flow direction is in this manner, feedback flow is in opposite manner. Don't get confused between parallel blocks and elimination of feedback blocks. Okay, in parallel blocks, remember, the flow of blocks will be in same direction if it is parallel blocks. If it is elimination of feedback, one flow direction will be in positive, the feedback loop flow direction will be in opposite direction. Okay, so as the next step, we can eliminate the feedback loop. So it is, we know the formula, it is g by 1 plus g into h, isn't it? So in place of g I have g2 g3, in place of h I have h3. So that will give me g2 g3 by 1 plus g2 g3 into h3. So here again I am getting one more feedback loop. So in place of g I have g2 g3 by 1 plus g2 g3 h3. In place of h I have h2 by g3. Applying that formula, that will give me the value of the block gain as g2 g3 by 1 plus g2 g3 h3 plus g2 into h2. So these two blocks in the next step are in cascade. Just multiply, that will give me g1 g2 g3 by 1 plus g2 g3 h3 plus g2 into h2. And in the last step, this is nothing but a feedback loop. So upon eliminating the feedback loop, that will give me my overall transfer function, that is g1 g2 g3 divided by 1 plus g2 g3 h3 plus g2 h2 plus g1 g2 h1. Okay, you can simplify this because this is g and this is h, we know the formula, so we can simplify, take LCM, and lastly you will get this answer. So the last sum for today's class, we need to find overall transfer function here. So as the first step, again I'll shift this takeoff point after the block. So according to rule number 6, shifting takeoff point, I need to multiply by 1 by g. So here I'm shifting this takeoff point after the block g4. So that's why I need to multiply here 1 by g4. So I multiplied. So these two are in cascade. These two also are in cascade. And this block is feedback loop. Okay. So first these two I'll connect in cascade. That will give me h2 by g4. These two blocks in cascade will give me g3 and g4. Eliminating this feedback loop, in place of g I have g3 g4, in place of h I have h1. Applying the formula, that will give me g3 g4 divided by 1 plus g3 g4 into h1. These two blocks in the next step are in cascade. That will give me g2 g3 g4 divided by 1 plus g3 g4 h1. So this is nothing but a feedback path. In place of G, I have G2, G3, G4 by 1 plus G3, G4, H1. In place of H, I have H2 by G4. So upon applying the formula, that will give me the value of feedback path as G2, G3, G4 divided by 1 plus G3, G4, H1 plus G3, H1, H2. So in the next step, these two blocks are in cascade. I'll multiply and get this value. Just this block is getting multiplied by G1. And lastly, elimination of feedback. Here H value is 1. In place of G, I have this entire block. So applying formula, that will give me my transfer function as G1, G2, G3, G4 by 1 plus G3, G4, H1 plus G2, G3, H2 plus G1, G2, G3, G4. So this ends my today's lecture on the first part of the block diagram reduction technique. So we have seen introduction of block diagram. In today's lecture, we have discussed what are the advantages, disadvantages and applications. We also discussed what are the various rules that need to be implemented during block diagram reduction technique, and we have also solved some tutorials based on these rules. In next class also, we are going to discuss some of the tutorials based on block diagram reduction technique. Thank you.